In the early 1980s, agricultural scientists decided to tackle one of the produce industry's most persistent problems. Tomatoes are round. Now, this might not seem like a problem to you and me, but for an industry shipping billions of tomatoes annually, those curved surfaces were a multi-million-dollar headache. Round tomatoes roll around in transit, bruise easily, and waste space in rectangular boxes. The solution? Make them square. The University of California, Davis took the lead on this wonderfully absurd project. Their agricultural department had already revolutionized mechanical tomato harvesting in the 1960s, but shipping remained inefficient. Rectangular tomatoes, they reasoned, would pack more efficiently, stack better, and suffer less damage during transport. They even calculated that square tomatoes would reduce shipping costs up to 30% per tomato. This wasn't some casual experiment. UC Davis assigned an entire research team to the project, spending years studying tomato genetics and growth patterns. They discovered that tomato shape is controlled by multiple genes, making the quest for squareness more complex than initially thought. The team worked with various varieties, trying to identify and isolate the genes that might lead to a more angular fruit. The researchers tried multiple approaches. One involved identifying naturally occurring mutations that produce more rectangular shapes. Another focused on selective breeding, crossing tomato varieties that showed any tendency towards squareness. They even explored using growth constraints, literally growing tomatoes in boxes to force them into square shapes, hoping these characteristics might somehow be passed on to future generations. Meanwhile, in Israel, science at the Volcani Institute were pursuing a parallel path. They developed what they called cubic tomatoes through careful breeding. They weren't perfectly square, but they were distinctly more angular than traditional varieties. The Israeli team focused on developing tomatoes that would not only be squarer, but would also ripen uniformly, another major concern for commercial growers. The produce industry watched these experiments with intense interest. Shipping companies calculated potential savings in packing materials and transport costs. Grocery stores imagined displays of neatly stacked square tomatoes. And even fast food chains considered the potential benefits for their sandwich assembly lines. No more round slices hanging over the edges of square bread. But nature, it turns out, has some strong opinions about the shape of tomatoes. Despite years of research and significant funding, truly square tomatoes remained elusive. The closest scientists came was developing varieties with slightly more angular shoulders and flatter sides. These improvements were minor compared to the perfectly cubic produce they'd envisioned. The technical challenges were numerous. Even where researchers managed to produce more angular tomatoes, these shapes often came with unintended consequences. The squarest varieties tended to have thicker skins, which is good for shipping but bad for eating, lower yield rates, and were more susceptible to certain diseases. It seemed that millions of years of evolution had some pretty good reasons for making tomatoes round. There were also practical agricultural challenges. Square tomatoes, when they could be produced, often developed irregular color patterns and ripened unevenly. The very characteristics that made them more shipping-friendly made them less appealing to consumers. After all, what good is perfectly stackable tomatoes if no one wants to buy them? By the late 1980s, enthusiasm for the square tomato project began to wane. The research didn't end in complete failure. It led to important discoveries about fruit genetics and development. Scientists gained valuable insights into how shape characteristics are inherited in produce, knowledge that would provide useful in other agricultural projects. While the perfectly square tomato remained elusive, the project sparked interest in reshaping other produce. Japanese farmers had already achieved notable success with square watermelons, growing them in tempered glass boxes to create perfectly cubic fruits that could be stacked like building blocks. Unlike tomatoes, watermelons proved amenable to physical manipulation during growth, though these square variations were more novelty than commercial success. They had to be harvested before fully ripe and cost 3 times more than regular watermelons. The fast food industry has been particularly invested in the square tomato concept. Burger King executive James McLemore later envisioned in his memoir that the company had closely monitored the UC Davis research. A perfectly square tomato would have solved their perpetual burger assembly problem, round tomato slices hanging over burger patties. McDonald's had even offered to fund part of the research, seeing it as a potential solution to standardizing their sandwich production. The quest for geometric produce didn't end with tomatoes. Agricultural scientists successfully developed cube-shaped oranges and teardrop-shaped strawberries, though neither made it to market. More practically, they created bell peppers that were blockier and more uniform, making them easier to pack and ship. These modified peppers became the standard in commercial growing, proving that some produce could be geometrically optimized. Perhaps the most successful geometric engineering came from an unexpected direction: the development of baby carrots. While not square, these uniformly cylindrical snacks were the result result of mechanical reshaping rather than genetic modification. Inventor Mike Urasek took irregular, unmarketable full-size carrots, turned them into perfectly uniform cylinders, creating a billion-dollar industry from what was essentially agricultural waste. The Square Tomatoes project's most lasting impact might have been psychological. It marked one of the first times the public had been aware about just how far agricultural science was willing to go to solve commercial problems. When the research became public knowledge, it sparked heated debates about the limits of agricultural modification. As one UC Davis researcher noted, people suddenly realized we could potentially reshape their food, and they weren't entirely comfortable with that idea.